So we just finished example 23.2, where we found the work that must be done by an external force to bring a third point charge from infinity to this point shown here, x equals 2a. And what we saw was that the value of the work was positive. So let's think conceptually why the external work would be positive to bring a positive point charge into this system right here. So if we're bringing it from infinity to this point, x equals 2a, this positive point charge is going to have to battle against the repulsive force due to the closest particle, positive charge right there. And then it's going to get a little bit of attractive force coming from the negative charge that's a bit farther away. And because the positive charge in that little scenario is the closest to the third charge that's coming in from infinity, overall, we're going to need to combat the repulsive force and therefore add energy into the system via external work in order to bring those particles close together. So that's how you should be thinking about this conceptually if you want to understand the sign of external work that must be done to move a point charge around, okay? So for external work, it's positive if you have to act against a net repulsive force, and the external work would be negative if the net force you were acting against was a attractive force, because it would already want to be close together, right? If there was already an attractive force. So you wouldn't have to do any work. In fact, you would get energy back. Let's look at this conceptual example. So consider this system of 3-point charges placed on the vertices of an equilateral triangle. What would be the total potential energy of this system? Well, we know that the potential energy is given by the constant K, which is 1 over 4 pi epsilon naught, the value of the charges divided by the distance between the charges. So if those two charges are positive, then the sign of the potential energy between those two charges will also be positive. And in this situation, we have 3 positive charges, so the total energy will add up to be positive, right? So that makes mathematical sense. So the total energy of the system is positive. Now, what about the external work, right? Another way to phrase that would be the work you would have to do to move the charges. And what if now, instead of like in the previous example, what if now you wanted to move these charges infinitely far apart? All right, so what do we need to consider in order to understand the sign of the work done? Well, back in chapter 6-ish area, right, we learned that the work done by any force is a dot product of the force vector with the displacement vector. So let's take a look at where the force vector would be pointing if we wanted to move these charges far apart. So the force vector would be the direction that we would be pushing these charges. So how about before I write that vector, let's write the force vector for this particle. Let's write the electric force vector, okay? And that's, of course, not going to be the direction of necessarily the direction of the external work, but we need to compare the force vector to what direction we need to push these, okay, in order to understand the sign of the work done, whether it's positive or negative. So I'm going to pick this top particle here, and I'm going to draw the directions of the force vector, the electric force vector. And so between the top charge and the left charge, right, they're going to experience repulsion due to one another. So this top particle here, he's going to experience a repulsive electric force pointing directly away from the particle on the left. So this is going to be the electric force due to particle 1. Okay, let's just call this 1, 2, and 3. And particle 2 on the top of the triangle, well, what is he going to feel in response to particle 3? He's also going to feel a repulsive force pointing directly away from particle 3. So that's going to look like this. And so just as we did in chapter 21, right, the net resultant force, the x components cancel, the y's add up. So the net direction of particle 1 is going to be pointing straight up. So if we were to kind of let this arrangement go, okay, something is holding them together right now in a triangle. If we were to take away that kind of force holding it together and let them do what they want to do, they're all going to fly apart. They're going to fly away from each other. And so the electric force is going to be in the direction of the displacement, right? If we were to let them go. But the question is asking, what kind of work would we have to do? Okay, so the work done by the electric force is positive because we want them to move far apart, which is pointing directly away. And the force direction due to the electric field is also pointing in the same direction, right? So we're going to get a positive dot product and therefore a positive value for the work done by the electric force. So what I wanted to draw was greater than 0, right? Work done by electric force. So knowing that and knowing the relationship between the work done by the field, right, also known as the work done by the electric force, what's the relationship between that and external work? Well, there's a negative sign there, right? So the electric work done by the electric field is going to be negative of the external work. And so that right there tells us that the sign of the work we have to do to move those charges apart is actually negative. And that makes sense if you kind of think about it this way. So the particles already have the potential to move away from each other. We actually don't need to put in any energy to move those particles apart. In fact, we're going to get some energy back because it's going to do it for us. Does that make sense? So the net sign, or the sign of the work you must do to move these charges infinitely far apart, is going to be negative. Okay? Right? They already want to move apart. They're going to move apart, and you're going to get some energy back because they're doing it for you. So we talked about electric potential energy, right? And I think we all have a good foundational understanding of that because of our experience with gravitational force and gravitational energy and gravitational potential energy. So now I want to define a new term relating to electric potential energy, and that's just going to be called electric potential, okay? We've dropped off the word energy, and that's because what we did is we've scaled energy by a factor of charge. So potential, which we denote by V, is potential energy scaled by charge. All right? In the same way that, remember, we talked about force, and then we said, okay, well, what if we scale the force by charge? That gives us electric field, right? And so we talked a lot about force, and then we introduced electric field as a scaling, as a force scaled by Q. Now we're talking about potential energy, and then potential is just the energy scaled by Q, where Q is the test charge, right? In both of those scenarios, Q naught is the charge that is the subject of the question, okay? The test charge, the one we're trying to figure some stuff out about. So we're going to introduce this concept of potential. The units of potential is obviously a joule per coulomb, right? It's potential energy divided by charge. And another word for that is volts. So that's voltage or volts, which you may be familiar with this term in your everyday life, right? That's how we charge our devices, as we plug them into a wall, and there's a potential in that wall that is required by our phones and our computers and our toasters. So it's a source, right? Your outlet is a source of potential energy for your devices. And since our devices take various different amounts of charge, we can scale that by charge and simply call that potential energy coming out of the outlet potential. So let's kind of look at how we defined potential energy. Remember, we said that electric force is conservative, and so therefore the work done was equal to negative change in potential energy. And so if we take that definition and we divide it by charge, what we get is the work done scaled by the charge is actually equal to a negative change in potential. Okay, so this is how we can come up with an understanding of what a change in potential is, right? A change in potential is simply the work done to move a particle from A to B, all right? And that's an arbitrary particle. So therefore, we're going to scale the work done to move that particle by its charge, and that's going to give us negative change in potential, right? That just ends up being VA minus VB. So VB is the potential energy per unit charge at point B, okay? And this difference here is the potential at point A with respect to point B. So that's VA minus VB. That's how we define the potential of A with respect to B. Okay, so these potentials are a function of position in the XYZ plane, okay, coordinate system. So I kind of showed you that analogy between potential energy and potential force and electric field. And what you'll notice here is that the way we calculate the potential is very, very, very similar to the way we calculate an electric field, right? We can just straight up write the potential due to a point charge as this equation right here, right? 1 over 4 pi epsilon naught, the value of the charge producing the potential, and then R is the distance from the point charge to where the potential is being measured. So these definitions are all nearly identical to electric field, except now we're talking about potential. And in the denominator, we only have a single R factor, not R squared. And similarly, if we have a collection of point charges, we can sum up the potential at any point in space by adding up all the potentials of each individual point charge and their distances from the place that we want to know what the potential is. And then finally, if we have a continuous charge distribution, right, we can use those same calculus techniques in order to find an equation for dq in terms of integrable variables. So if we had a line charge, our dq would still be equal to lambda dx or dy, wherever our line charge is located. Okay, and now instead, of course, we're going to be integrating with respect to r instead of r squared, and we express the r in terms of our integrable variables. So r would just be the distance from that dq to where we want to know the potential. I want to give you a sketch of what potential is, right? It's kind of right now not super clear. We're kind of speaking about potential abstractly, and so I want to kind of draw a picture to give you a better idea of what potential is. So if I have a positive point charge and a negative point charge, I can draw immediately the electric fields, right, of those charges. And we all know that the electric field always points towards negative charges, right? And towards negative charges, away from positive charges. So if this is our equation for potential, I'll write it in a different color. This is our equation for potential, right? Where R is the distance from the point charge to the place we want to know the potential. You will note that regions of constant potential would be circles of radius R, right? Distance away from the point charge. So what I'm drawing here in these concentric circles are regions of constant potential. And right, they're all a distance R away from the point charge. And if we draw circles of constant radius around those point charge, around that point charge, everywhere on that circle will be a distance R away and thus have the same potential. So potential lines are pretty much going to always be perpendicular to electric field lines. I said pretty much, they always are. Okay, that's actually a rule. They're always perpendicular to field lines. So now what would be the value of VA or VB? Well, the value would be given by this, right? If Q is positive, R is always positive, then this VA and VB over here, they're going to be greater than 0. And how about their relationship to each other? Well, VA will be greater than VB. Why? Because R is smaller for VA, right? The radius is smaller. It's in the denominator, which is going to make the voltage higher. And so what about here for the negative point charge? Well, if we draw our circles again, our regions of constant potential, we call this VC and VD, okay? These are all going to be negative. Why? Because Q, that's creating that potential, is negative. And what about the sizes or magnitudes of the voltage at point C and point D along those circles, right? Well, VC is actually going to be more negative than VD, therefore smaller, but its magnitude is going to be bigger, right? But it's going to be more negative and therefore smaller than, I don't know why I wrote VB, I meant VD. Okay, so VC is actually going to be smaller than VD. That's because it's more negative, right? It's going to be a bigger negative number. R is smaller, but Q is negative. So you're just going to get a big old negative number the closer you get. Okay, so that's the relationship of potential, regions of equal potential, giving you an idea of the sizes of potentials, right? Where it's more positive, where it's more negative. So if you're given some potentials in a problem, you can kind of imagine them as being really close to a positive charge or really close to a negative charge, okay? And perpendicular to the electric fields created by those respective charges. So I gave you a kind of physical picture of potential, where it's positive, where it's negative, where its magnitude is higher, where its magnitude is lower, where it's more negative, okay? What can we do with that information? Well, in some problems, we may have some knowledge of the electric field, like we do for point charge, right? We kind of know everything we need to know. If we see a point charge, we can already write down everything we need to know about it. We know the direction of the E field, we know the magnitude, all right, given by the equations in 21. So sometimes, instead of calculating the potential this way, it may be easier to use the electric field knowledge, okay? And so what I want to do is I want to show you the connection between potential and electric field. And so in order to elucidate that connection, we're going to start with the work done, okay? And so the definition, strict definition of work done by any force, whether it's conservative or not, is going to be F dot dl, where dl is the displacement that we're moving along the force direction. And if that force is not constant, we're going to have to do an integral, okay? And so that we're just kind of writing the most general form of work done. So don't let the integral scare you, right? This is just the most general form of work done, integral f dot dl. So what we can do is we can substitute what we know about f. And what we know about f is that it's equal to QE, right? So if we plug in QE into f, well, we can pull Q naught out because it's just a constant. And what we see is that the work done is equal to just integral E dot dl, you know, with Q naught factor in the front. And so, well, now what if we scale everything by Q naught? Well, if we divide both sides by Q naught, we get this, which we saw on the previous slide, was equal to the difference in potential between point A and point B. And then we got rid of that Q naught on the right-hand side, and we're just left with E dot dl. So here we have a direct relationship between potential and electric field. The change in potential, or the potential of A with respect to B, well, it's equal to integral E dot dl. So the displacement along the electric field direction, okay, that's going to be equal to the change in potential. And so a lot of times it may be easier to, you know, do this integral, or maybe we can just automatically know those two potential values and subtract them. So, you know, depending on the problem formulation, this may be a better equation to use versus this set of equations of just, you know, directly getting the potential from charge and distance. So if we kind of write that out more, you know, there's a couple ways we can write a dot product, right? So we can just say that it's the magnitude of the electric field vector times cosine of the angle between E and dl times dl. So that's how we turn that into magnitudes and drop our vector notation. Okay, so note that there is another way to write this equation, and that's using, right, the property of integrals, where if you switch the order of integration, right, you pop a negative sign in the front. So we can rewrite 2317 as VA minus VB equals negative E dot dl, okay? So you just have to pay attention to the order that you are solving your integral, your definite integral. So with that in mind, we can see another set of units for electric field, right? Previously, we were using electric field units as newtons per coulomb. Why? Because we divided force by charge, right? And that gave us electric field, so that's a newton per coulomb, okay? Well, now if you look at this equation that I just showed you, equation 2317, you can see that there is actually another set of units that we can use. If you were to divide both sides by this dl, which is a distance, okay, you get a volt over meter. And that's another unit for electric field, a volt per meter. All right, and that comes from using this definition to kind of either figure out what the E field is or figure out what the potential is. And when we're talking about potential, energy, and electric fields, it's going to make a lot more sense to use volts per meter, especially when you consider how we make electric fields. Okay, so there are some video demonstrations that you can look up for electric fields. And one of them that I do in my in-person lecture is we supply a whole lot of energy to a pair of conducting sharp points. All right, and let me kind of draw you a little picture here. So if I have two needles and they're made of just some conducting metal. And I hook them up to a power supply, okay? You'll learn very quickly that this is a circuit diagram for a power supply. It's a pair of parallel lines with one short, one long. We'll talk more about that in the next chapter. And so I'm going to supply a potential, which is basically a source of energy for all the electrons in this circuit. And if I supply enough potential, I'm going to have electrons moving in this circuit here like this. And then they're going to encounter kind of the end of this metal piece. And if there's enough energy supplied, I can get them to kind of jump to the other conducting point, okay? And what's in the middle is air, right? This thing is sitting in air. And what you get is that kind of electric spark, and it's a very loud noise, and you get what looks like lightning, basically, right? And so lightning is essentially a whole bunch of energy given to some electrons. Well, not some, but a lot. And they just have all this energy that they're just going to be flying through the air, seeking a place to go. And usually that's the ground or the earth, right? And you can visually see them as kind of like blue, or depending on the gas that it's in, whether it's air or pure oxygen or some other gas, it's going to light up the gas and cause ionization and turn it different colors. So in the room demonstration, it was bluish, purple, because of the nitrogen and other elements that are floating around in our air that we breathe. And so what we basically did is we created an electric field here, right? We created an electric field by supplying a huge potential over a very small gap here, okay? So that's just kind of an illustration of this new set of units, volts per meter for electric field, right? Electric fields are created by giving energy to a system over a distance. Okay, that's how you get an electric field produced. So let's talk about another unit or another quantity. And I hope it doesn't, add to your troubles, but it's actually supposed to help with some calculations, because this, we scale by Q, right? When we talk about voltage, right, we're scaling the energy by some charge Q. Well, in this course, that Q is pretty much always going to be an electron, okay, unless we're talking about a specific case. But as we get into circuits in the next chapter, electrons are the charges that are going to be doing everything for us. We're going to be, applying a potential to electrons. We're going to be having electrons move through a circuit. And so it makes sense then to talk about the potential energy in terms of units that involve an electron's charge. So if potential is potential energy divided by charge, well, if we kind of scoot that charge over there, we can see that potential energy is expressed by charge times a voltage. Okay, and since that charge is an electron and the subject of all of our problems, except for some couple specific ones, we can then just say that, well, if this is joules and this is Q times V, well, we could also just call this unit, instead of calling it joules, we can call it an electron volt, okay? And so 1 electron volt then is defined as the energy required to move an electron by 1 volt across a difference of 1 volt, okay? So the energy required to move an electron through a potential difference of 1 volt is 1 eV, which is 1.602 times 10 to the minus 19 joules. So if we have a unit of energy, let's say that it takes, 50 joules to move an electron across a potential. Can we figure out what potential that would be? Well, it takes 50 joules to move an electron across a potential that's unknown. So we have E, right, the charge of the electron times the voltage, which is unknown. So if we divide both sides by E, then we can figure out what that potential is, right? Because the right-hand side is an energy, the left-hand side is an energy, so those must be equivalent. But if we express that energy in terms of charge of an electron times the voltage, well, we can just divide both sides and we'll get voltage on the right-hand side. So there'll be some other problems and examples that will do, that you use this unit for energy. Okay, so let's do this example where we can kind of put these new concepts to work. So we have a proton, which is a positively charged particle, same magnitude as an electron, but it's positive. Moves a distance of 0.5 meters in a straight line between 2 points A and B. The electric field is uniform along this line, and we're given the electric field magnitude, so we're given knowledge about the electric field. And it's in the direction from A to B. Find the force on the proton, the work done by the field, and the potential difference VA, VB. So let's do that. So I'm going to draw a sketch. It's always the first thing you should do, right? We got a point A. We have a point B. We know our electric field points along that direction. And the magnitude of that electric field is 1.5 times 10 to the 7 volts per meter. And so this proton is moving a distance of 0.5. Let's see if I can get a different color here. There we go. I like red for protons, right? So this proton is going to be moving this distance, d, of half a meter. What's the force? Let's do part A. What's the force on that proton existing in the electric field, right? As it moves along from point A to point B, it's going to be bathing in an electric field value of 1.5 times 10 to the 7. So the force is just going to be the charge, which is positive E, right? 1.602 times 10 to the minus 19 times the value of the electric field. So we can calculate that quite easily. Times, I'll just move it down here, 1.5 times 10 to the 7 volts per meter, okay? So that gets us a value of 2.4 times 10 to the minus 12 newtons, okay? A small force. So, part B. What's the work done on the particle by the field, right? So we have some expressions for that. We know a couple things. We know that the work done is, well, we can always use this equation, right? Force times displacement. And this is the most general expression. But what we have here is a force that's constant, right? So we don't really need to integrate anything. The only time we need to integrate is if this force changed with position, right? If this force had different values along that line. It doesn't, it's constant, right? Because E is constant along this line. So therefore F, force, is gonna be constant along this line. And so we can just express this integral simply as force times displacement. So what's the force? Well, we just figured that out in part A. And what's the displacement, right? It's moving from point A to point B a distance of 0.5 meters. And so we can get the work done by the field as simply F times 0.5. And so that gives us basically this number divided by 2, right? Part A divided by 2, which is 1.2 times 10 to the minus 12 joules. And so just for fun, what if we wanted to express this in units of potential? Okay, EV, right? In units of EV. So what we would do is to convert joules to EV, we would take the joules, and we know that 1 EV is 1.602 times 10 to the minus 19 joules. Right, that's the conversion factor from the previous slide. And so then we're basically going to be dividing 1.2 times 10 to the minus 12 by 1.602 times 10 to the minus 19. And we're going to get 75 mega EV. 7.5 mega EV. In other words, 7.5 times 10 to the 6 EV, which we could call 7.5 mega EV, where mega is 10 to the 6, okay? And so that's just, I'm just kind of demonstrating that because it might come in handy in part C. So part C, we're going to be finding the potential difference VA minus VB. So there's a couple ways we can do that. Recall that VA minus VB, well, we can express that as the integral negative A to B, or flip that B to A, right? E dot dl. Okay, so the other way we could approach this is we could recognize that the potential required to move the proton from A to B is equal to the work done divided by the charge that's moving, right? So we figured out what the work done was already in part B. So we don't really need to perform this integral. We wouldn't need to anyway since E is constant, but it's going to be ending up the same way, right? We can kind of write it both ways. So work divided by charge. Well, here's the work right here, right? Expressed in EVs or in joules, and divide it by charge. So let's do it both ways. So VA minus VB is 1.2 times 10 to the minus 12 joules. Divide that by the charge of the proton. Coulombs, right? Well, that's going to give us this number right here, right? But in units of volts, right? Because we already did that. We did 1.2 times 10 to the minus 12 divided by 1.602, but that was different units, right? That was a unit conversion. So now we're dividing it by coulombs. Joules per coulomb is a volt. So we're going to get 7.5 megavolts, or times 10 to the 6 volts, right? No E there. Because we're not finding units of energy, we're finding units of potential. So in other words, what you could do is by inspection, if we instead found the work using EV, right, we saw that the work was 7.5 times 10 to the 6 EV. Well, if we divide that by the charge E, we really don't need to do anything in the calculator. Well, let me just divide it by E, right? That's going to make it more clear. If I divide that by E, the E's go away, and I'm just left with 7.5 times 10 to the 6 volts. Okay, so there's the utility of reporting your energy in units of EV, because then if you're asked for the potential, well, just drop the E, right? If you're asking for the potential that a positively charged proton would experience. So that's just kind of, right, a quick demonstration. And so now let's look at this. Well, this integral here, the integral goes away because E is constant anyway, right? We're just left with electric field times a distance. Magnitude of electric field times that distance. And sure enough, that's what we did up here, to find, where did we do that? Oh yeah, we did that right here, right? This was charge times electric field, and this is a distance, right? So E times D divided by Q gives me my voltage back, right? So that's how they're all related. So this is just E times D, which is a voltage. And so we could have just done that to get this same number right here, right? And let's just do it. So the value of E was 1.7. Let me just double check. 1.5 times 10 to the 7. And that's going to be voltmeters, right? Times the distance traveled, 0.5 meters. And so there we go. The meters cancel, and we're just left with volts. The value being 1.5, 10 to the 7 times 0.5. Sure enough, is 7.5 times 10 to the 6, right? Volts, which is the answer we got over here doing it the other method. So I hope this example illustrates the connection between the parameters, voltage, work, potential energy, electric field, and charge, right? And EV units of energy. So, take some time to look at this and kind of really get comfortable with how all of these quantities are related. They're simple relations, but they can get confusing because there's so many possibilities, right? There's two ways to express voltage. There's two ways to express energy, so it can get a little bit tangled up. So we just did this example, and I want to show you some other examples that I'd like you to do on your own. If you get stuck, you can click on this link down below for the video provided by the publisher on how to complete this example. And so here, this may look familiar, right? We did this back in chapter 21, where we were asked to find the force at different points. I believe maybe we even found the electric field at different points. And now we're asked to find the potential at different points. And so you're going to use your equation. I'll just kind of give you a little rundown, right? You're going to be using the equation for the potential of a point charge. And you're just going to be adding that up, right? This is going to be your R's are going to change. You're going to make sure you use the proper Q. If you're depending on whether you're finding the potential due to the positive charge or the negative charge, okay? And so you're going to be adding the potentials due to the positive and the negative charge at point A, the potentials due to the positive and negative charge at point B, and then the same thing at point C. And in this example, which I'd like you to do on your own as well, is we're going to be finding the potential energy that's associated with placing a third point charge at points A, B, and C. Okay, so you're going to be calculating the total energy of, let me see, potential energy. Yep, exactly, at A, B, and C, due to the interaction of this +4 with the point charges Q1 and Q2. And so this example I kind of want to briefly do with you. It's really quite easy. It's just getting comfortable with the kind of integral notation that we looked at earlier, right, in the way that we defined potential difference from point A to point B. So by integrating the electric field as in this equation, where we had VA minus VB equals integral A to B E dot DL, okay? Let's find the potential VA minus VB using that integral, okay? And so, well, this is a point charge producing an electric field, and we know everything about this electric field already, right? It's 1 over 4 pi epsilon naught Q over R squared, right? So that should be kind of like memorized by now. That's the equation for the electric field of a point charge. And so we're going to pop that guy in this integral here, okay? And well, let's take a look, right, because we have a dot product. So let's see if we can get rid of that dot product. Well, what's the direction of the electric field due to this point charge? All of these vectors are in the R direction, right? The radial direction. If we're considering, polar coordinates, since this is kind of 2D right now, right? The R direction is the radial direction. And so so this is going to be in the R direction. I'll say R hat. Okay, that's the unit vector direction of E. What about DL? Well, where are we moving? What direction are we moving this? What direction are we trying to find the potential along? Okay, we're trying to find it between point A and point B at infinity. Okay, and so that DL is going to be in the very same direction as the electric field, right? In the R hat direction. So the direction of DL is also in the R hat. And so therefore that dot product goes away and just becomes the magnitudes. So VA minus VB is going to be integral A to B of E dl. And so let's express that in units of R, right? We can leave E as 1 over 4 pi epsilon naught Q over R squared. And then our DL is going to be just dr, right? A small piece of distance in the R direction. And so our variable of integration is R. And if we move all these constants outside of the integral, you'll see that the only thing that we're really integrating here is 1 over R squared, which is a very simple integral to do. Okay. The indefinite integral, 1 over R squared, is just negative 1 over R. We're going to evaluate that from A to B. And what's A and what's B? Well, A is A, right? A is some point A, but B is infinity. So let's just keep that in mind. B is infinity. So that's going to be negative 1 over B minus a negative 1 over A. All right, we get Q over 4 pi epsilon naught, just taking our constants out. So we're going to get negative 1 over infinity plus 1 over A. 1 over infinity is 0, okay? So we are going to get, simply, if I just kind of rewrite my variables again, Q over A, which is just VA, right? Potential at point A. So that just kind of shows you how we, can use integration to find the potential if necessary, right? So in this case, it may have been easier to just write down, since we know what's VA, right? Well, the definition of potential of a point charge is 1 over 4 pi epsilon naught Q over R. Well, what's R? It's the distance from the point charge to the place we want to know, and that's A, right? So if we plug in R equals A here, we get the exact same answer as that integral provided us. Okay, so this is kind of just showing you how to approach this integral, because let's say you were told that the electric field had some other functional form. Okay, well, you would just pull out all of your constants and you would make sure that your E field is in the same direction as your DL so that you could drop your dot product, and then the function you integrate just may or may not be 1 over R squared. It may be something else, and you would just perform that integral and you would get the potential, okay? And it's only because the potential point B was at infinity that we got that 0. So what I want to kind of show you, this is also another good problem to do, because this will take into account the conservation of energy. All right. It's a good kind of throwback to chapter 6 topics where, the total potential the total potential energy plus the total kinetic energy equals 0, okay? So, and that you use that to help you find speed, because remember, K is 1/2 mv squared. All right, so that's a good example to do. There's a few examples in this chapter, and I'll let you know which ones that you don't need to worry about too much. So just for the sake of time, you don't need to worry about 23.8. What I will tell you that 23.8 illustrates is the electric potential outside of a sphere. This picture here is the electric field outside of a sphere, which you may recall we did this example in chapter 22 with using Gauss's law, right? And we found that the electric field outside of a sphere is the same value as if that sphere was condensed down into a little point charge at the origin, okay? So this is just kind of a reiteration of that, right? The electric field inside a conducting sphere is 0 because all the charge resides on the surface of the sphere. Well, what about the potential, okay? Well, the potential, you may, it's a little bit counterintuitive. You may want to say that the potential is 0 inside the sphere as well, since the electric field is 0. But in fact, the potential inside this conducting sphere is a constant value of 1/4 pi epsilon naught q over r, okay? So everywhere inside the sphere, the potential is the same, okay? So anywhere along any point in the sphere, the potential is 1/4 pi epsilon naught q over r, where r is the radius of the sphere. And then it's only when you start getting outside the sphere that the potential starts to decrease. So it starts to behave like that point charge again, as if this sphere, solid sphere of radius r, is condensed into a tiny point charge at the origin, such that little r is the distance from the origin, and so you can see the potential gets smaller and smaller, drops off as 1/r, the farther you get away from the surface of the sphere. And so that's what that example illustrates to you. So here I'm just telling it to you as a fact. If you were to do any of these examples, I would just do 2310. Don't worry about ring symmetry, okay? We'll go back to parallel plates when we get to chapter 24. So if you're going to do any of these examples, I would look at 2310 for infinite line charge, okay? And so they're going to be the most helpful for you to help you answer some homework problems. As far as tests in the future, I will let you know exactly which examples to look at to study for the exam, okay? So that's why I'm kind of telling you right now that I'm not going to be testing on ring geometry. I'm not going to be testing on spherical geometry. I'm pretty much going to be testing on line charge, one-dimensional geometry. But that'll be more clear when I put out the study guide, okay? So don't write it down right now, okay? Let me just, because I haven't made the test yet. So I'll definitely give you guys a study guide about a week and a half before the exam. So the last thing I want to touch on, this is going to help you with one of the last homework problems. Well, what we saw earlier, right, is we saw a relationship between potential and electric field, and we saw that that relationship was had an integral involved, right? And basically this let us go from V to E. How to find V, finding V from E, right? That's what this relationship helped us do. Find the potential from the electric field. Well, guess what? You can actually go the other way, all right? If the potential is known, so if you have some, you were given an equation for potential, okay? Could you find the electric field from it? The answer is yes. And the relationship is going to be the opposite of integration. It's going to be derivatives, okay? And so we can get the x component, right? Because the electric field's a vector, okay? So we get the x component of that vector by doing negative partial derivative of the potential with respect to x. We get the y by doing negative partial derivative with respect to y. negative partial derivative with respect to z to get the z component. Okay, and so I had someone in one of my lectures when I did this lecture last week, said that they weren't super familiar with partial derivatives. So if that's the case for you, I'm going to give you an example of what a partial derivative is. And it's really, nothing crazy. I'll explain to you what it is right now. Just trying to pull up. All right, let me pull up a blank screen here. So a partial derivative is a derivative, except that we are only taking the derivative with respect to the variable in the denominator, and we're ignoring any other variable in the equation. So let's say that we had a potential that was a function of a point in Cartesian space. And let's just say it was, all right, let's just say, it has some combination of x, y, and z, okay? So a partial derivative, taking a partial derivative of v with respect to x, would be going through each of these terms and treating every other variable as a constant and only taking the derivative with respect to x. So this first term would end up just being 4y squared, right? Because the x just drops off since it's only got the factor of 1, right? The derivative of that second term would be, well, let's just make it more exciting. Let's turn this to a cubed, okay? You're going to get 18, right? 3 times 6. I'll just write it out. X squared, z squared, right? Because we're just taking the derivative with respect to x, and it's a factor of 3. So, and then finally, there's no x term in the last term, so that's going to be a 0, right? That's just a constant. So derivative of a constant is 0. And so in total, that gives us 4y squared plus 18x squared z squared. So we can do the same thing for y. The first term, we have a y squared, so that's going to be 8xy. The second term, we have no y's, so that's going to be 0. The third term, we have a y cubed, so that's going to be 21y squared. And then finally, with respect to z, we got a 0. And then we have a 12x cubed z, and then a 0. Okay? And so, well, we're not done yet, right? If we want to turn this into electric field, recall that the electric field in the x direction is negative delta v delta x. So that's going to give us negative 4y squared plus 18x squared z squared. Our electric field in the y is negative delta v delta y, which gives us negative 8xy minus 21y squared. And then finally, negative 12x cubed z for the z component, right? So if we were going to write this vector in vector notation, the electric field vector, I'm going to write it up here. This is what it would be, okay? It would be all that junk, all that business here. Did I get, this should be a minus, sorry about that, right? This is a minus. Minus 18x squared z squared I hat plus negative 8xy minus 21y squared j hat plus negative 12x cubed z k hat. Okay, so that would be our electric field result. So you'll need to use this technique for one, like the last homework problem. And if I'm going to test on this technique, I will let you know in the study guide. But this will give you a kind of a quick overview in partial derivatives. So that's how the electric field is related to the potential. And this example demonstrates that partial derivative. So you may want to look at this. The derivative will be with respect to r. And so that is the end of this chapter here in the end of Unit 2. I did want to show you this cartoon that I drew that will kind of show you the relationship between all the variables that we have discussed so far. And so, right, we talked a lot about, especially towards the end of chapter 23, how to go back and forth between potential and electric field. So now if you look at this triangle, you can see the relationship between charge, potential, and electric field, right? Those are the key quantities. And all the rest of the quantities can be derived as, with respect to these quantities right here, Q, V, and E. And so way back, in chapter 21, we saw that if we had knowledge of the charge Q, that we could get E, right? We could figure out what E was if we knew Q by writing down the equation of a point charge, okay? And then we just saw now that if we have knowledge of the charge Q, we could get the potential written down right away too, in the same way as E, right? Just 1 over 4 pi epsilon naught Q over R. And then finally, at the end of chapter 23, we were able to go back and forth between potential and electric field, right? We can get potential from electric field using an integral, and we can get electric field from potential using derivatives. Okay, so that's kind of, there's other directions here, but they're out of the scope of general physics too, so you don't need to worry about that. If you are interested, I can show you the full schematic, but we're not going to be testing on it. It's just kind of out of the scope of this. But so I wanted to leave you with that at the end, a kind of a cute cartoon that lets you see how everything works together. And of course, right, what's kind of embedded in here is the fact that potential energy scaled by charge is potential, and that force scaled by charge is E, right? That's kind of embedded in there. So you can always go back and forth. You can always find F and U very easily by just multiplying potential or electric field by Q, okay? So next up we'll be talking more about kind of the technology that we have in place to use these quantities to our advantage in chapter 24 when we discuss capacitors.